So in science and anything that's science-like, I suppose I had a 15, 60 students that were restaurant management majors. But even in everyday life, error reporting is useful. I'll go over that a little bit. But if you publish a paper with the results and you don't quote a plus minus on it, nobody cares. And they won't read your paper. And also, like, let's say that we have a quantity that you can measure called the meaning of life. And somebody has published a paper that says that the meaning of life equals 5 plus or minus 0.01. So you run an experiment. So this is this is right now the accepted value. And this we decide that we're hot stuff, and we publish that the meaning of life is actually 4.96, but then we say plus or minus 0.05. And that means that our measurement could be 5.01 or it could be 4.91. Whereas the other group, it could be 5.01 or it could be 4.99. So we have not produced a better measurement. So in fact, scientific papers, they spend their whole time like you have an intro, you have an explanation of the result, and most scientific paper, at least in physics, are 4 pages long. And so by the halfway through the first page, you spend the whole rest of the time explaining to people why they should believe your plus minus. Now, if the thing you publish, then there's one more wrinkle to it. Like let's just use volume for an example. So we're going to do L. We have to decide on a plus minus L, the length plus minus the width. Length, L is length, Harry. The width, and then the height. Because, of course, we all know that the volume is equal to the length times the width times the height. Okay. And then what we want to say is that we got volume. That part's easy. But now we have to say plus or minus what? And that's one of the things we're going to learn today. Okay. So let's new slide because I just remember there was the definition. Okay. So a systematic error, if you didn't find it in your reading, is whoops, SY. Wow, I badly screwed that. Oh, I had it right. What am I doing? Gosh. You know what? I pulled in my parking space this morning, and then I look around to gather up my stuff, and I left my freaking computer in my backpack all the way back in my house. I had to drive all the way home. And then my wife was still there, so I had to let her know what I was doing, so I couldn't just hide the fact that I was a moron today. So a systematic error could be some mistake you've been making. Um, let's say or for example, there was this famous example of this. This is a major error, but it's still a systematic error. This group in Europe said that they'd measured the speed of light faster than the accepted speed of light. And they said, look, we don't want anybody to believe us. We just can't understand this. And what happened is they had a fiber optic that was not plugged in all the way. So it seems like that wouldn't matter. But when you're measuring the speed of light, and it's a fiber optic, if it's too far away from the connector is pulled out a little bit, the signal's not arriving at the right time. In the case of something like us, if we have a ruler, oh, this is great. where are my rulers? We might forget that, well, not in the case of a metal ruler, but the a lot of these wooden rulers, because they could be damaged, you might forget that the zero is not at the very end. So you take all your measurements and you use the end of the ruler as your zero. That's a systematic error. So it's either a mistake you made, or a mistake in your technique, or a mistake in technique, or you might have some fault in your machinery, in your experimental machinery, some fault in the gadgets. That's a systematic error. And then a statistical error, statistical error, in a nutshell, is a counting error. And and you use this. I don't know how much we're going to do this, but this is if you have um, let's think about this. Oh yeah, so if your estimated plus minus is very large or impossible to define, like we say, well, I'm rolling this marble down the track and it's going to leave and it's going to land somewhere. Yeah, I had a source of error that it rattles. A source of error is that it slips, or the person launching it doesn't release it with 0 meters per second. But it's impossible to put a number on it. So when you have, you're going to have to measure something like that. What you do is you make a graph like this. So this is like, say, 5, 4, and this is 6, 7, 3. You measure something over and over again, and you get various numbers. And if it falls in between these pairs of numbers, you put it into here, into that box, and you get a distribution. And this is called a bell curve. It is a bell curve. You may have heard of that. A normal curve. And this is the measurement, and the width. This is our plus minus. That's a statistical error. So it has to do with the spread of our measurements. And that's good enough for us for the time being. Okay. Accuracy and precision I'll get to in a moment. Okay, so in the real world and in protecting ourselves, as informed citizens, we need to know how to look at numbers. And so if we look at month 1, McCain is in the lead. And in month 2, Obama's in the lead. And of course, the so-called spin doctors, Obama's campaign people, are saying, oh, Obama took a big jump and he's solidly in the lead. But a good polling agency is going to publish their plus minus. So if you include the plus minuses here of 4, that means nothing has changed from month 1 to month 2. So you get to roll your eyes and you say, well, you're full of shit. We don't know what happened. And so this is about importance of, what's going on here? Wow. Okay, there it goes. Come on. One thing is it's hard to see where the cursor is when I'm using my pen on my tablet. There it is. Uh, shit. Oh yeah. No, everyday life. It's not just scientific measurements, so it's not completely irrelevant for you guys that I don't know, maybe some of you are kinesiology majors, but and another way to think of it is like say, oh, there was a 300%, somebody says the news, 300% increase in deaths. So 100% is double, 200 is triple, and 300 is times 4, right? So what happens if there was one person who died last year in 23, and in 2024, 4 people died? Well, that's not a big increase, right? But it's still a 300% increase. And more importantly is what's the population? Is that one person 1 out of 100, 1 out of 1,000, or one, like if it's Los Angeles, it would be 1 out of 4 million. So if they don't say what's the population they're describing, not all of this is not very meaningful, right? You've got to have the real, in this case, they quoted it in percent, but if you dig down, you may find that it wasn't that big of a deal. And if you dig, and it's really they're obligated to tell you what's the population that it quoted against. For example, now this morning, my wife was reading an article that said that somehow California has become ground zero for corrupt officials. And last year there was 500 um, people arrested for corruption. And I said, okay, well, how many were arrested the year before? Or is that in all of California? Is it elected people, or is it people who, the point is that this wasn't very, she thought, wow, that's a big number. But unless we know other pieces of information, there's no way to judge it. So these are examples of error reporting. And the other thing it's the example of that we didn't have in the pre-lab, it's called normalization. And normalization is just so that you can, it's a way they treat the data so you can compare it. So in the case of this lab, we were going to calculate the density, and that's a normalized variable, and that we can use that to compare anybody. We can compare our density reading to anybody else who measures some arbitrary piece of material. They don't have to care how big or little it is. They can measure the volume and the mass, and they can get the density. Okay. We already saw this. That's weird. Oh, I went the wrong direction. Yeah, and so global warming, and when they report things, I mean, I personally accepted it. I mean, it's hard to argue it doesn't actually affect. E&M radiation, I don't see that as, I don't know, this is a bad example, I think, in a way, because there's no plus minus. You know that um, anything that's less than the sunshine, like the ultraviolet, doesn't affect you, so it can't hurt, can't cause cancer. All right. Okay, accuracy and precision. I'm a little, I'm not, well, these bits in the yellow here, I'm a little skeptical, but accuracy for certain is how close we are to the truth. And of course, we don't call these systematic errors, but systematic errors affect our accuracy. And as this person states, it can take a long, long time to determine what your exact estimation is. And this is like I do gravity wave research, and we're trying to measure a length of 10 to the minus 18 meters. There's lots of error that associated that we have to remove from the measurement. And also that like we have techniques, and we're going to learn a simple one today. A lot of times we don't even know what the true value is, but the error estimate it helps people to say, well, it's probably right because we can reduce the error. And then precision is basically number of decimal places in a really simple. So if I measure something to be 5.0, even without a plus minus, if somebody else says 5.00, their measurement, this is more precise. So for us, these are things that we're not going to deal with a huge amount, but this is, you're supposed to leave this course understanding what that means. So I've got this. Oh, yeah. Of course, if I'm going too fast, you should be like taking some token notes here because I'm trying to keep it all relevant to the lab and what you're supposed to take away from the lab. This here you don't need. Uh, this not really. This bit here is really important. It's good you need for the lab. Right. This is important for your lab logbook. This would be optional, 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 and then this one is should have. So if you want me to go back, just let me know. So much easier to do this in person. So when you're doing it on slides in Zoom, you have a tendency to put up too much material. Here we go. Yeah, this is a big one that they try to slide past you, the spin doctors and people who don't make an effort to be unbiased. Mark Twain said that there are lies, there are damned lies, and there's statistics. And the point is that you can present numbers and have them say anything you want unless you provide the normalization. So maybe this is important for the notes, only in the sense of you say, okay, 300% versus 1 and 4. These are the years. And then, so this is what would you call it? A statement about a health statement of the county, say. And somebody is trying to say that the health department is doing a shitty job. So you got some newspaper reporters trying to say that the health statement of the health department, let's say, or an article. And they're saying, oh, there was a 300% increase in deaths. And so we got to cut their funding and people can't get raises, that they got their raises taken away. But if you look closely and you notice it goes from 1 to 4, and then you say, well, it's a population of 1,000 people, you can do an easy calculation that number will bounce around randomly a certain amount, and with no identifiable cause. So you need to know, percents are fine, but you also need to know the absolute number, and you have to know the population. So when you have all of this, you would say your data is normalized, but people will hide some of that stuff because they want to put forth a certain viewpoint. Now, I forgot if I might have moved way too fast on this one. The lesson here is, again, you see that Obama, there's been McCain lost a point and Obama gained 3 points, but plus or minus 4 means that's not larger than the uncertainty. So you can't make a judgment. And by the way, this is precision. So these measurements are of a certain precision. Probably they're accurate, but in the case of accuracy in a poll, that has to do with they only call like 1,000 people. So part of the survey, when they ask you if you're going to vote for Obama or McCain, they ask you if they can ask you a bunch of questions like how old are you, what's your race, how much education you have. So, they could call 1,000 people and they could all be male by random chance. They could all be white and they all could have PhDs. So they could call 1,000 Dr. Harrys. And you wouldn't trust, not that you don't trust, that you get the results of who they vote for, but it wouldn't tell you what the country's going to do. So in the case, the normalization here comes from them doing due diligence, that they corrected the bias of their 1,000 people that they surveyed. Okay. All right. So here's a good way to think of accurate and precise. So the best one is the third one, right? All the measurements are very close to what the true value is, which you don't always know. And they're tightly grouped together, so they don't have much variation. So if I made, and this is sort of statistical, this one would look like that, and this one would look like that. But they both have the center of the circle. This one would look like this, and this one would be very sharp, and you'd think you did a good job, but it's not the right answer. It's not the center of the circle. So that's what accurate and precise is visually. Okay, let's pause a moment. All right. So just yell if you want me to go back. Oh, I know what. Okay, well, here it is. Right. So what we're going to do is, well, one thing, a definition. Let's make a definition up here. Definitions. Well, there'll be more, I suppose. So a primary unit, there is length, and there's mass, and there's time. And for us, that's meters. Oops. meters, kilograms, and seconds. A derived unit is a combination of primary units. A derived unit is, let's see, let's put it down here. Combination, and it could be a combination of primaries, or in some time, well, it's always actually at root, it's always a combination of primaries. Okay, so I'll take that back. And for example, density, that's the symbol rho, that's a lowercase Greek rho, equals volume, no, it's mass per volume. So yeah, kilograms per meter cubed. And mass is a primary unit, volume isn't. So it's mass times length squared, cubed, excuse me. So it's meters cubed. So the units are kilo, and we don't have a special name in this case, kilograms per meter cubed. Sometimes if it's really common, we have a special name for the units, but we just quote it as kilograms per meters cubed. Okay. So it looks like that's all our background. So our objective is to learn about the proper technique of taking a measurement with a ruler and then estimating the uncertainty on our measurements. Somehow have so we're gonna learn about how to properly use the ruler, how to read it. How can we estimate the uncertainty on a measurement? Because normally we would be using the scale too. And then if we have we used our, and these are usually primary units. So if we're going to create a result of we have to get a final uncertainty of our measurement, of our derived measurement, because we're going to combine primary units into a volume for us. So we need to make an uncertainty on the final product. So you can just, I wouldn't copy a word for word, but just about. That's not a problem. Propagate uncertainty to a final uncertainty of a derived measurement. Oh, okay. It's not that bad. All right. Let's see what else. I left myself some room. Okay, so our procedure is pretty straightforward. We're going to measure the length, width, and height of a block. And we're going to estimate the uncertainty on each one. So I haven't written every word. We're going to measure L, W, and H of a block. And we're going to estimate uncertainty on each one. So that's all kind of summarized, up here. And then let's see if I can fix this up. No, it doesn't want to work. Okay. All right. Now I can make it a little smaller. It's amazing what you learn during a pandemic. Okay. And I should have moved this down a little bit. Let's see if I can do it. No, doesn't want to work. Come on, baby. There you go. Let's move that down here. Estimate uncertainty. Uncertainty of LWH of, and then calculate the volume and plus minus volume, aka the uncertainty on a derived unit. All right, how long have I taken? A little bit too much time. Okay. In a normal lab period, I probably wouldn't have spent so much time on that background, but part of the 1560 and 1570 is supposed to be about helping people to learn how to use this math and science to defend themselves against idiots and judge newspaper articles and things. Okay. Just yell if you want me to go back. All right. So you see, we have two rulers. And by the way, give me a minute here. I want to Yep. Let's copy and new. Uh, yep. Delete this. Oh, let's get rid of that. I'm gonna put this up. I apologize. That really should put this up for you guys because you can. Is that gonna work? Looks like it worked. I want to make something that's small enough when you print it that it'll fit in your notebooks, your logbooks. Okay. I'll send this. So what you can do is you can sketch some notes and for this picture, and you can get this thing and print it out and paste it over that, which is normally not is a normally a no-no, but we'll let that slide. Oh, what the heck happened? I duplicated it. I didn't want to duplicate it. I just wanted to select it all and make it smaller. And we'll just do it the quick and dirty way here. And then if I don't do this now, I'll never remember. All right. Oh, physics 1570, not this. Yeah, if we have, you're perfectly welcome to any reference document or lab manual I post. You're welcome to print and paste the diagrams, but don't print and paste any of the text because that's plagiarism. 1570 lab 01 ruler technique. Okay. Save. And then save it as a PDF. Yep. And then this is the fastest way to get. Oh, I know even a faster way. But I better do this for the people who aren't here. Diagrams, lab 1, and then file upload. This. There we go. Oh, I have to publish it. All right, so to save yourself some time, you could sketch this out and then you could put in that nicer picture later. Let's see. There we go. Okay. So today we're going to do something a little different than this because we're not going to use the zero, but we reduce error by using that zero. We put it exactly on there, right? And normally we'd be really happy in that if the end of the candy cane landed on one of the black lines, but that just rarely happens. So how do you read? So reading a ruler. So you look at what you're trying to measure, and what you always do is look look to left for first printed line. So here, that would be 4. Here, it would be 4.2. All right. And then of course you write it down. That's your first digit. First printed line, first digit. Well, it could be 2 or more, but this is the beginning. It's the first, it's to the left of the decimal place generally. Then you have to estimate next digit. So in this case, I can sort of say, all right, it looks like halfway, and it looks like halfway right there. And this is one of those times where we're kind of lucky because it sits right in the middle. So why don't we just take, oops, I want to, oh, this is a copy paste of a picture, so I can't move that line. All right, we'll just go with it. So I'm going to say that this is, I guess I could say it's 4.25. And I could say that about this one too. And okay, so far so good. And now we have to estimate the plus minus. Now, you might have been told that you take 1/2 of the smallest increment. So the smallest increment here is 1 centimeter. And so that rule would say plus or minus 1/2 a centimeter, but that would make it either 4 or 4.5, right? And my eyesight's better than that. But at the same time, when I look at this with nothing to help me, I realized that this could be 4.20 or it could be 4.30. Is everybody okay with that? Because I don't have any extra lines in there to help guide my eye, I don't feel like I can do better than that. So that looks like a plus or minus then of 0.05, which I also think is a little optimistic. So it's not rocket science. I just decide on what that could be, and that's what I settle on. So I look here at the lower ruler, and we see right away it's no way 4.20 or 4.30, right? Because it would have to be right exactly on one of those lines. So right off the bat, our error estimate has to keep us in between those two lines. Well, it's an informed guess, Angela. That's it's sort of, but it's informed guess. Don't tell anybody. But it's a guess and we're setting limits as to what it could be, right? And that's what an uncertainty is. It's how much of that measurement are we not sure about, right? So that's why it's kind of a guess, right? That's a great question. So we see how now with the better ruler, it's got to be less than plus or minus 0.05. And I look at that and I say to myself, well, it's pretty much in the middle, but okay, I will allow, if I could find Mr. Cursor, where are you? Come on. Yep, there we go. I will allow that this could be 4.24 or it could be 4.26, right? Because I look at there and that's pretty much in the middle, but maybe it's a little bit to either side. So I'm going to say that this is plus or minus 0.01. Excuse me. So excuse me again. The ruler on the bottom gets us better precision. Or if we be close, if it, okay, I don't know if I can duplicate that. Let me see. I might be able to. So yeah, so it's hard to move. So that one's on the right side, right? So now we say that's our first line to the left is 6.2, and it looks like it could be 6.28. So we know that it's no way 6.30 because then it would be on the line. And we see that it's above the halfway point, so it couldn't be 6.25 either. So in this case, I would still say I could allow myself plus or minus 0.01. Did that help, Angela? Oh, you're welcome. I'm glad it worked. Okay, let's put this back because we're going to use it in a little while. Close enough for government work. Okay. Right. Now, I don't expect you guys to, every time you make a measurement, you do this once and now you need to write this. Whenever you take data, you have to write down that we estimate plus or minus. So we have a ruler. It's marked out in tenths of a centimeter. And we estimate that we can get we can go to 1/100th of a centimeter or 2 decimal places, something like that. And we say that we can do plus or minus 0.01. Now, believe it or not, I always tell students that it has to pass the LOL test. So the LOL test is if we make it too big, then people laugh at us because, as you know, as we said earlier, our measurement has less meaning to compare to other people. Probably we wasted our time. So people are going to say, who the hell gave this person grant money and who let them up on the stage? So they laugh at you. By the same token, if you make it too small, then people are going to laugh too because they're going to say, oh, this person's just making stuff up. And if you make it too small, you're going to have to spend a lot of time proving to people what you did. So your uncertainty, and that's why I did these, how big could it be or how small could it be? Because nobody will argue with me about that one, right? Somebody might say to me, oh, 0.01 really should be 0.02. And if somebody really wanted to push on it, I might say, okay, I'll make it 0.02. So my overall point of it is that when you're taking measurements, you have to estimate an uncertainty and you have to justify it. So what I would write here is that we have a ruler that's marked out in tenths of a centimeter, and we believe that we can guess the where it is plus or minus 1/100, which is also a tenth of a millimeter. So tenth of a millimeter, maybe that is too optimistic, but so it might be set. But again, when I look at this one, since it's exactly in the middle, that one isn't. I'm pretty, so maybe I could say, maybe I might relax it because that'll certainly pass the LOL test, right? Nobody's going to fight me on that one. So there's no absolute right way to do it. there's guidelines. So it's not completely a guess. It's like I said, it's an educated guess, but it has to be justifiable. In physics 1570, I just want you to write down a plus minus. One could argue that if the measurement falls right on a line, then you know it more precisely, right? Because it couldn't be plus or minus 0.02 because it wouldn't be on the line anymore. But for our sake, you decide on an uncertainty and you can use it for every measurement. I just want you to do it. I want you to decide, make a note of it, and just say, well, why you did it. That's all. And done. And we'll get back to this. And let's take a look here. So we started talking a little bit about this. So one thing we went over was the basics of just simply using a ruler. And so somebody texted me a great question, right? So when you put an object down there, you look for the mark. So in the case of ruler A, the first one was the 4, right? So the general rule is you when you use a ruler, when you put the object and you try to line it up. Most of the time, we line up with 0. So for this ruler, that's 4. And then we have to, since there's no other marks, we have to estimate. And of course, we by eye can sort of break it up. And yeah, and we went through a whole discussion of this. Let's go back because it's already in our notes. And or is it here? Yeah. So we pick we get that number, and then we have to estimate the next number, and then we went through a discussion here, and then right here we noticed, oh well, we can get a better number. Okay. And then I believe we talked a little bit about this, but I'm just going to reiterate. So there's other things now. There's technique, and I think I showed this to you. I just don't see it written down in my notebook here. So either I didn't do it, or I was so busy that I didn't write it down. Yeah, I'm getting it. It's coming back to me now. Now, my wood block that I actually used is a little bad for this because it's a children's toy. I got a huge amount of these. They're beautiful maple blocks. It has this chamfered edge, those to be a little safer. So I'm going to use this wood block because it has nice even edges. And this is when I was hoping we would be talking about the density. So I got 3 different wood blocks, but since we're falling behind a bit, which is my fault, but what can you do? So the idea was that when you take a measurement, there can be a certain amount of error in. So when I look at this, to me, and now to you guys, the way it looks, it's exactly at 15. But if I were to go like this, and in fact, let's see, I need to, let's make this bigger still. Oh yeah, so you can see it now. It's not quite, if from your point of view, it looks like
it's more like 14 point, it looks like it's more like 14.9. But when you look straight down at it, and the idea is what you do is you try to make sure that, like if I go here, see, I can see the end of the block. And so as I bring it up and I go, now, of course, if I go too far, there's no way of knowing anymore, right? So it's a bit of a trick to go just far enough and then start going back, and just till the edge, the side of the block disappears, then I know I'm looking straight down on it. And that's called parallax. And, you know, it's a big fancy word, and you can sound real smart saying it, like supercalifragilistic, if you've ever seen Mary Poppins. It's summing up this word, and you've got a lot to say. So that's called parallax. So we talked about taking readings with the ruler. And one of the things, and there's other ways, there's other things you could think of about how you might make the measurement better. So let's see, 2, 17, 21. Yeah, I have to get this. How can we make this better? Yeah, if I make it bigger, I can't write small enough to fit it where it belongs. And the time 11:33, and my initials. So parallax, and then we finally figured out how to use the ruler here, but I am going to cheat, and I'm just going to make a box. If I was doing this, I would use my ruler and draw it out on the lines, right? Of the spreadsheet. Oh, I want spreadsheet. Forgive me. The my logbook. And let's make the outline a little heavier, just to. There we go. So now, if I had me a ruler up there, and somehow this feels familiar. I did this somewhere, maybe not with you guys. And so when I want to take my measurement, I want to make sure that, oops, my eye is directly above. And we don't want it to be here. This is the good eye. And this is the bad eye. And if we look down perpendicular to the block edge, we minimize error. And if you were to be writing up a formal report about some measurement, this is the kind of thing you have to describe to people. When we took this data, which I think you probably want to write down in your logbook, when to minimize error, we made sure to look straight down. And this is called, this error here that's introduced, again, this is called parallax error. So we try to use rulers that have more, okay, slow down, to minimize error, blah, 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 blah. Okay, so we talked a little bit here about the ruler itself. So equipment, we can use a better ruler. So to get better measurements, and this is kind of, I guess, a summary that we could talk about later, but it also helps us as a Advanced organizer, better measurements, we use more precise ruler, right? We saw that when we used the ruler with the millimeter marks, we could get more decimal places, or use more precise ruler. And then, and so this is basically on the heading of instruments or equipment. And this is why it's important to describe your equipment. And then technique. And so in both cases, it's important to write down how you took the measurement. So we took a ruler, we dropped it onto a block randomly. We made sure to, and we measured that we took our overhead straight down view to reduce parallax error. And parallax error is the apparent, you get a number that's the correct number, but if you don't look straight down, if you look at an angle, you have a possibility of a false reading, and it has to do with the thickness of the ruler. If you think about it, another way to minimize it, of course, would be to use a clear ruler. And one of an advantage of a clear ruler is that, and this really hopefully will dramatically show us the parallax error. Let's see if I can do that. So I will claim that I have it directly on the 12, right? But if I go way over here, yeah, it's obviously not on 12 anymore. It's very, I don't know if I can focus that. Oh, it's a little better. Yeah. And if I bring it over here, yeah, now it starts looking like it's more than 12. It's kind of hard to see. But you can just take your own ruler and convince yourself. There you go. And so and another cool thing about the clear ruler is that in this case, I'm trying to, oh, this is nice because this ruler has the markings on the bottom. Wow, so that's really nice. So that makes it much better, right? So I can even accentuate the parallax error by putting it with the markings on top. Oh, cool. Get together like this, even though I've been a little scatterbrained on you guys. Oh, this is cool. Now you see the two, and of course I have to stay on the screen somehow. There we go. And oops, I moved a little bit. Well, it's a 3, not a 2. And then if I'm like this, glare, where is the glare coming from?
Professor, we can't hear anything. It's lagging.
Yes. You just can't focus it. Oh man. Thanks. Thanks.
What's that? Yep. All right. So you should be able to hear me now. Yes. The video. Okay. I got to slow down. Yeah. I bought this Bluetooth headset here, and it's supposed to go 20 hours of talk time. I got to return it. Okay. All right. Oh, yeah. So again, this camera is not doing the job, but so. But I didn't realize that this thing has the marks on the bottom, which is very nice. That because the parallax error in this case comes from the thickness of the ruler. And this is for a piece of crap ruler. That's pretty cool. Okay, so we went over, yeah, a little bit of this. So let's motivate this, what's going on here. And so, excuse me. So let's, oops. And this one has last time, so I will make a new slide. And so we have 2, 17, 21, and it's 11, 42, date, time, initials. Okay, so we have, let's say we have two numbers, right? So first of all, we have for the length measurement. So here's an example error calculation. So we determined the length by having an L1 and an L2, and they each had a plus minus. So we want to say, all right, L, if we say L itself is equal to L2 minus L1, great. And so let me take one of my numbers from my spreadsheet, if I can find it easily. Oh, that's the ticker tape. So I have 17.2 and 3.4. So I have L1 equal to 3.40 centimeters, and L2 is equal to 17.20 centimeters. Now you notice I quoted a larger error than what we were quoting. So I'm saying both times plus minus 0.2, and we determined it to be 0.02, but because I didn't give you guys the best ruler. If you looked at, 0.2, if you look at the, I have to do single line cross out, plus minus 0.2 cm. And if I'd have provided you with the proper ruler, if we were in class, whatever. So now we plug in 17.20 centimeters minus 3.40 centimeters, and we get let's see, that's 8. Oh, cross out. 0 from, I could have kept that. 0 from 0 is 0. 4 from 12 is 8. 3 from 16 is 13. 3 from, is that what my spreadsheet says? Let's see if I can check my math, 13.8. Oh, I got it right. Okay, so how do you assign a plus minus to it? Well, there's a couple things we could do. We could say that we said plus or minus 0.2, right? So let's make this 17.4 minus 3.2, and we can say, all right, now it's 0.20. 3 from 17 is 14. Or we could go the other way and say 17.00 minus 3.6, which is going to be 0.4 and 13.40. So then we say, okay, the final answer is 13.80 plus or minus, let's see, 0.4, huh? 0.4 centimeters. Now, in this case, it's not real dramatic, but we should think about this and say to ourselves, I don't really think that whenever I take a measurement, I don't really think that I'm always this far off. I think that most of the time I'm going to get a pretty good, I'm going to get the real number. Excuse me. And so we have this table, and I decided we'll just focus on the formulas that we need. And I'm just looking for it. Let me copy it, huh? Control C, error propagation short form. And these formulas here, and I talked about it a little bit last time, I think. And I use this table when I write a paper. And so we're going to use this one here for this. This is for addition. So F equal, whatever you're determining equals something like this. And it could be minus as well. It doesn't matter. Little a times capital A. And I'll explain the terms in a minute. And it's either plus or minus little b times capital B. And the sigma here, the definition of the sigma here is our plus minus. We went over this last time. And then a little a and b are constants, just in case, like if you did 2 pi plus something, constants. Now, sigma, this is, for us, is always going to equal 0. And it just means that if there's some kind of relationship between the two measurements, but we know that the two measurements don't have anything to do with each other, so we don't need the sigma AB. So at the end of the day, and for the most part for us, little a and b are going to be 1. If there's ever a chance it's not, we'll go back over it. So what this becomes then is, let me think it through. Oh.
Do you mind zooming in a little bit for the formula, please?
So we're going to say, for our case, we have L. Oh, of course, I'm sorry. I can't. How's that? Oops, why did that happen?
Okay. I think it froze.
I lost the logical thread here. Right. So what? You can't, what, can you see what I'm working? It's got some lag going on.
It's good.
Can you see it now?
Yeah, it's perfect.
Okay,
thank you.
Great. All right, so hold on. Oh, okay, great. So when we say that the two things are independent, I finally thought of a good way to think about it. If we think of a right triangle, right? And we think of this as sigma capital A and sigma capital B, then we're going to say that the sigma on F is the hypotenuse. Because remember, we said the two of them are not dependent on each other. And in math terms, that means that the measurements are orthogonal. And in XY, that means they're at 90 degrees to each other. So we know the Pythagorean theorem says that sigma f squared is going to equal sigma a squared. And then we just simply take the square root of it, and you see how we end up with something that's not quite the worst case scenario and not quite the best case scenario. So let's, and then the final answer is sigma f equals sigma a squared plus sigma b squared to the 1/2 power. So now what we do is we plug in our actual numbers. So it's sigma L equals sigma L1 squared plus sigma L2 squared. And we do the 1/2 power again. So that was 0.2 squared plus 0.2 squared square root. So that's 4 plus 4 is no 0.04 plus 0.04. And so it becomes 0.08, square root of 0.08. And so then we just take our calculators. .08 square root, and it becomes 0.28. So you see how now we would expect it to be a little bit bigger, but than 0.2, but we really wouldn't expect it to be as big as 0.4. So at the end of the day, then we have L and sigma, remember, is plus minus L equals to, what do we get? Cm plus minus 0.28 cm. Okay. Do you see my mouse screen, my mouse moving around? No, Tamara?
It like takes a while to catch up. Maybe like 7
Let's
seconds.
try.
Yeah, I think
Stop.
even when you hear us lagging or
Okay.
like there's I think that moment.
Wow. Okay. So, well, luckily that's what's nice about having it written down here. Yeah. Okay. So the motivation here is that we need to add the errors some way that kind of reflects the fact that we're not going to, every single time we take a measurement, do the worst possible measurement. We expect that our measurement, for the most part, is going to be good. And that's what doing the Pythagorean theorem thing does to help us. Excuse me. Okay. Can I make a new page? Can I go to a new page? I'll just, well, you know what? I'll wait for somebody to yell at me to go back. New slide. Oops. Yep, of course.
Oh, okay. You got it.
And I need to scroll it down, I think. Yeah. That's the bottom. Now, remember, you guys should add some descriptive words in here, okay? Because I didn't add any no. Yeah. Okay, so here's what it's on. It's on Canvas, and you go to oops, scroll up. Excuse me. So go to short form because you'll just lose your mind if you look at this one. The math is really heavy. Propagation of uncertainty. And so for physics 1570, we use, right, so there's the minus, but they're basically the same formula. We use, these are for adding and subtracting things, and then we use for multiplying and dividing, but notice each time they're the same formula. Okay. And they're also in the spreadsheet too. So one last thing we need before we move to the spreadsheet is recall that we talked the volume, the plus minus on the volume. So I just wanted to reiterate that in terms of my inspiration to use the Pythagorean theorem idea. Okay, so we have 2, 17, 21, it's 11, 59, and there's the date. Okay, so we have update on the plus minus volume determination. Yeah, I can, in nation. Imagine I learned how to where to put a hyphen when I was in grade school because we didn't have, even when you have a typewriter, you have to figure it out, right? Word processors were on the distant horizon. Okay, so excuse me. We have L plus minus L, whoops, plus minus L, W plus minus W, and H plus minus H. And this is, we've already seen this, L times W times H. And once again, if you were to do you could figure it out and you'll see a huge swing. So give me a minute, let me think about this. Right, we could do plus volume equals to L plus minus L times W plus minus W times H plus minus H. And we could do a negative vol you'll know if you do it, at least do one of them, you'll see it makes a huge number. And again, we just don't believe that we're that inaccurate all the time. So you remember from last time, the way to understand this is to remember the definition of fractional error. Fractional error. And fractional error is the plus minus of a value divided by the value. And we sometimes use the symbol, this lowercase delta. And why would you do that? And why do you not do it when you do the plus minuses? Excuse me. In the plus minuses, when you add and subtract numbers, first of all, the sig figs comes from the number of decimal places, but for us, it's always going to be the same. But let me think about this for a minute. Why do we use we don't use the fractional error for plus minuses? I have to think on that one. I know why we use it for the multiplication process, because what happens is if I measure, so for example, if I measure 50 centimeters plus minus 1 centimeter, we would think that this is pretty good. If we were to measure 5 centimeters plus or minus 1 centimeter, we'd say, well, yeah, meh, it's not that great, huh? But if we now want to sort of use our Pythagorean theorem idea, we are not going, our answer is not going to reflect the fact that this is very good and this is so-so. So if we look at the fractional error, 1/50 or 1/5, now we can obviously see that this is a much better measurement. And if we did it earlier, what if I got to think about that one. That's a good point. I need to motivate that one. So now in the case of length times width times height, remember we had that it's not exactly Pythagorean theorem anymore, because we have 3 variables. And it's, so this is of f, and you can go back in your notes to look at it. So what we do now to get the we get the fractional error of v, and that equals the fractional error of L squared plus the fractional error of, W squared plus the fractional error of H squared. And this makes sure that each one of the errors, depending on, again, this weights them properly. This way we know this is a great measurement, but this one here is not so good. So it's going to contribute more error to the final answer, and it should. Now, the only thing now we have to remember is that we don't want fractional v, we want plus minus v. So we just had to remember that this delta v also equals plus minus v, so let's box this, over v. So what this implies is that plus minus v equals to capital V times the fractional V. So now, yeah, I'm hoping this gives you a better feel for what's going on here. Whenever you have things that you measure, that one measurement has no effect on the other measurement, we do this kind of Pythagorean theorem thing. For adding and subtracting, we simply use the plus minuses or the sigmas. And for multiplication and dividing, we use the little delta, the fractional error. And that's why it's in the table. So for addition, subtraction errors, and this is called error propagation. For addition, subtraction, error propagation, we use the plus minuses or the sigmas. For multiplication, division, error propagation, we use the fractional errors, which is the plus minus value divided by the value. So let's put plus minus value. And this is how when you tell people you made some measurement, and like you say, you measured the volume of the block, you can tell them how good of a job you did. All right, so I'm going to switch the spreadsheet, so you're going to yell at me to go back